In this video, we were just going to look at a couple of very straightforward things. The first thing is how to find the area of a sector. Again, this shape here is sector. It's part of a circle, it's a fraction of a circle. So if you had your angle in degrees, you would do that angle divided by 360 and then multiply it by the area of a circle, pi r squared. Now if it's in radians, that equation becomes like this. It's a half r squared theta. If theta is in radians, it's a much simpler equation. You can see this equation here. But remember, this expression here is if the angle is measured in radians. This expression here is what you would need to use if the angle were in degrees. So it makes this kind of a question here fairly easy to answer. All we have to do is to take the radius 4.8 and the angle 1.08 and put them in for r and theta into this equation here to get the area of the sector. Okay, so if we do that, the area is going to be just a half times 4.8 squared, that's the radius squared, times 1.08, that's our theta, the angle. And if you do that calculation, I hope you get 12.4 square centimeters. In example 5, if you're told that the arc is of a certain length, sometimes questions might ask you to do something complicated, like get the area from that. Now, it's a little bit of a problem because we know that the area is a half r squared theta. Now, in this case here, we don't know what theta is. We're told what the radius is, we're told what the arc length is, but we don't know what theta is yet. However, we can use this formula here, which involves the arc length and the radius and the theta, to get theta, because we're given the radius and we're given the arc length, so we can put those values in here for s and r and calculate theta as a result. So if we do that, substituting those values in for r and theta, for r and s, we'll get this expression here, and then just divide both sides by 8.35, we'll get roughly, approximately 1.497. And then we can use that expression, that 1.497, in this expression here. We know what r is 8.35. We know now what theta is, we've just figured it out, it's 1.497. So if we put those values into our expression, we'll get this. Doing the calculation should give us 52.19 square meters. Now, another place where you might see radians used is in the expression of angular speed. That's something that's used quite a lot in physics. And if you go into the calculus, you'll probably see at some stage something to do with angular speed. It's basically the angle that you move through, let's say in a second, over a certain time. So if you do a full rotation in 5 seconds, you would be doing 360 degrees in 5 seconds, or you would be doing 2 pi radians in 5 seconds. That can be converted into an angular speed. An angular speed, the notation looks like this. Angular speed, we have this special letter that looks like a W. It's actually the Greek letter omega. And all you have to do for omega is to divide the angle that you're moving through by the time. Now, usually angular speed is measured in radians per second. So if you're told that you've got something that's an angular speed of if you're asked for the angular speed of something that's moving at 4.8 meters per second around a circle of radius 25 meters, what you would have to do is figure out, well, what angle is it moving through every second? And a way of doing that is just to use this formula here, right? That the actual linear velocity is equal to the radius times whatever the angular velocity is. And that's just another way of writing these equations that we have up above here. Okay, so the linear velocity, that's the actual velocity, is equal to the radius times the angular velocity. It's just another way of expressing the arc length formula. It's just everything divided by t. So if we do that, using that expression there, we'll get 4.8 equals 25 times omega. Right? The velocity was 4.8. The radius was 25 meters. So the angular velocity here, the angle that is moved through every second here, is 0.192 radians every second.